So here we are today. All I'm planning to do is demonstrate some projects today. We've covered all the chapters in the book I really planned to cover. This last day, I'm probably going to just demonstrate some more machine learning. It seems the transition method needs to be run at 1,000 times something. That could be that attack, yeah. Anyway, yeah. So let's talk about these projects, ED 207, 210, and 220. That's my goal today, is just demonstrate these. So here's ED 207. Now this one is, there's a virtual machine you have to run, and normally you have to have VMware, although I figured out how to do it on the M1. It's going to be a 32-bit Alpine Linux code running, and so you get this thing called TinySploit and run it, and it's a very small machine. I was very happy when I learned this. I actually wrote a bunch of hacking projects for one of the classes years ago using machines made this way. With something like 30 megabytes, you can have a running Linux machine to hack into. And if you do it on the M1, you have to emulate the Intel processor, but since it's so small and efficient, it works. So you can boot the thing up, and when you do, it will tell you the URL. You can see it there. 192.168.64.3 is the URL. That's all you need, is that URL. So this machine runs a web server, and you can attack it. And I'm just going to shove this to the side and make this instructions a little smaller and show up the website, which is here. Okay, so there's what you see, 192.168.64.3. It'll be a different IP address on your machine, but here's the deal. And they point out you can send a GET request like this. If you get /AAAAA, then you'll find an overflow. So that's all you have to do. So you can do it with the same procedures that we've done here. Let me clear. All right, so let's take a look at attacks. So if I, let's clear again. All right, and now make this bigger. All right, so if I do ls, I've got various programs here to get you started, and these are just straight from my instructions. So the first one is fuzzing. Get. Let's start with get. Clear cat get. There. All right. So this one just creates a socket object, and then connects to that machine at that IP address and that port, and then it just sends a get A. And I forgot to put in the /A, but it doesn't seem to matter. That's nice. So I get A from of HTTP 1.1 and that host. So if I run this, it gives me an HTTP 200 OK, which means, by the way, it's a kind of funny web server. Without the / I think that might not make any sense. But anyway, so it gives me a reasonable response, so it did not crash. All right, and let me put the virtual machine here on the left so we can see the effect. We'll see some things go by there when we make it crash. So now, let's try fuzzing it. Clear I wanted. All right, so if I cat fuzz. All right, so this one is exactly the same program. I just put a times 1,000 here, so it's going to send 1,000 A's and then complete the request. And so if you run that one, it doesn't return any 200. And over here, the console shows segfault at 41414141 on the bottom line there. So that's nice. It gives you an error message that's kind of helpful. So that means some of those 1,000 A's ended up in the instruction pointer. So that means it's going to be exploitable. So the next thing is to try fuzzing it with different amounts of input. So here, I just input from the user the number of A's, and then I put in that many A's. So fuzz 2. All right, so 100 does not crash it. It works. So 200 does crash it. It seems to automatically restart, which is handy. So if I go back to 100, it's okay again. So now I can just narrow it down. 150 does not crash it. 170 does not crash it. 180 crashes it. So somewhere between 170 and 180 is the crash. So that's because the server is probably just like a one-liner Python script or something. It's not a real web server. And it must automatically restart every time it crashes. So it must have written the code to do that. I mean, that's when we did this before, we'd run it in a debugger, we'd have to manually restart it after each crash. But I guess for purposes of this hacking, they made something that will just automatically restart every time.
I think there may be like a software restart or something
Yeah.
very fast.
Yeah, that's right. So I think it's built in. If it crashes, just restart.
And I think servers is doing the same thing.
Yes, some servers will do this too. Yeah, I know if you on a Windows server, you can specify if you run a service what to do when it crashes, and you can tell it to restart, and you can even tell it to restart only 10 times before quitting. Things like that.
Could you do the same thing with your servers?
With what?
With the server that you use?
Yes, I think a lot of servers do automatically restart when they crash.
The one that you use, instead of crashing and then you without service for
Well, I don't know. I guess you could, but I'm not sure how to write that code. You know, in principle, you can. Yeah.
instead you have to restart it every a day or so later.
Yeah, that's right. In principle, I could do that, and a lot of people do at enterprise level. They make things that automatically restart for that reason. Yeah, that's why when my servers go down, I have to manually restart them. And you can make ones that automatically restart and even that automatically recover from image. It would be a good idea. All right, so anyway, then we can get to the EIP. So here's one that puts 160 and then 20 carefully chosen characters, just a non-repeating pattern, A, B, C, D, E, F, G, H. That's 8 times 4, that's 32 more characters. So put in 160 A's and then 32 more characters, so that should make it crash. So if I run this one, it does crash. And I can tell from the screen here it crashed at 45, 46, 46, 46. So I should be able to target the EIP. EIP2. So it was 45, so that's A, B, C, D, E. Okay, so the number I saw here was 45 and then 3 46s. This is 1, 2, 3, 4, 5. Okay, so the last E and the next 4 characters are what made it crash. So this should be the EIP. 1, 2, 3, 4 right there. And I guess to make it easier for next time, I'm just gonna, I guess I could just count these. 1, 2, 3, 4 times 4 is 16, 17, 18, 19. All right. So 179 A's, and then EIP, I'm going to put in a 1, 2, 3, 4, and see if it enters the EIP. There, and so now I'm going to send get, and then attack, and then EIP. There. So if I've done it right, I'll get a 1, 2, 3, 4 in the EIP. That's my EIP2. So Python 3, EIP2, and oh, that's right. I remember this because I'm using Python 3. I have to use bytes for everything. Oh, right. And this is EIP equals, not play. Okay, there. That should do it. Clear. Okay. There. And segfault is indeed at 31, 32, 33, 34, so now I can target the EIP directly. I can see there that I've hit it. Now, I don't think I'll continue demonstrating it all live. That gets you started. Now you just go through the same process we've already done. So once you've fuzzed it, once you've found control of the EIP, then you can just make a remote shell. So you target the EIP precisely. Okay, now you have to identify the bad characters. Add like 0 to 128 to find bad characters. Find out what bad characters there are. Test for alphanumerics. Then you can create a shellcode. So I found after you find the bad characters, which turn out to just be 0, 10, and 13, the kind of thing you'd expect. Null bytes, carriage returns, and line feeds are the bad characters. So, all right. Now you can, in this one, I logged into the machine and ran GDB at the other end. So that's one way to do it. But anyway, then you're able to insert a breakpoint, disassemble the code near the crash, and I think you end up putting in a remote shell. Yeah, there you go. You have this sort of thing. And then you can find an exploit. You'll find out it does not even have address space layout randomization. And so you can then put in a dummy shellcode the way we've done it before. Oh, and I think the point is this one does have address space layout randomization. That's the trick of it. So I'm not going to go through it in detail, but that's the point of this one. You're going to need to use ROP. So you'll have to generate shellcode. And use, I think, a trampoline bounce to get there. So let me find there. Testing ROP with dummy shellcode. So here's the important point. This one here is probably worth trying out. So let me see if I can get this demonstration set up. Let me find out how to log into that machine. Log in, okay. I did this the wimpy way. You can do it without logging in, without being able to run a debugger on the target, but I didn't do it that way to make this easier. Username root, password exploit lab. Okay. So you can connect. Let's make an SSH session. Root at the same address, which is 192.168.64.3. All right, and yes, an exploit lab. All right, now I'm in. Now, I can run a debugger for the PID that's run the process. So I do netstat minus pant, pant, P-A-N-T-N will do. All right, and so here it is. Here's the listening process on port 80. So it's process 672. So I can run GDB, I don't want the banner, PID equals 672 to connect to the running process. Okay, now I'm connected to the running process. And now when I crash it, I should see it in GDB. So when I go to my other window and I run, say, this, then that should have done it. And let's see what I need to do here. C to continue. Oh, it's not running anymore. I think I have to hit C to continue. Yep, now it's running, and when it continues, it crashes with 1, 2, 3, 4. All right. So now I've seen it. All right. All right. So GDB doesn't allow us. So we want to examine the memory just before the crash, but GDB won't let us step backwards, and the EIP contains garbage. So how do we find the location of the code preceding the crash? In GDB, I can do it with the next I command. So there's one technique. Let's quit from here and connect again. Okay, and now I can do next I to just step into the code. And now it's not going to proceed until it has data, so I have to send it this attack again. All right, and so now it proceeded. So now I can just step through lines of code, like 10 at a time, and I can repeat this until the program crashes. This is one real sloppy way to trace through code, but it works. So I just hold down the Enter key. I'm jumping through 10 lines of code at a time until it crashes. And I don't, okay, let's try, I think I'll do 50. All right. There we are. So now I know it crashed here. So here is an address before the crash. All right. Now I can put a breakpoint there. B star there. Let's get rid of this. B star there. All right, and now I should be able to restart it. Right, and the only way I did it here was by leaving and coming back. So let's put this in the clipboard. Quit, yes. Go back in, put a breakpoint there. Now run, or continue. All right, now send the attack again. All right, and now it doesn't crash, but it hits the breakpoint. And now I can disassemble code near the crash. So I can do X, examine 10 instructions at this address. All right, and there's some code. Here's the step I'm at. And now I can step forward until I find it. So if I hit another enter, it'll go down further. And you see here's a return from a function. So if I have a classic buffer overflow, it'll crash on the return. And that may well be the case here. So I can move my breakpoint up to that return instruction, or the one before that return. So I'm going to get this instruction here. Suspecting that the breakpoint is the end, I'm going to break it here. So I'm going to quit, enter again. Now I'm going to put a breakpoint there. And now continue. Now send the attack. Okay, and now I seem to be right at the point where it's going to crash. So I should now be able to look at the info registers. Okay, same thing we've done before. All right, so ESP is here and EBP is there. And we can examine it. The ESP is 6D0 to A28, so it's pretty big. So I can X/200X ESP. It's going to end at BA28. So there's all the A's I put in. And BA28 is here. So that's the end of the stack. And as you can see, there it is, and there's the 1, 2, 3, 4 I put in. So this is a classic buffer overflow, and there's the stack. And now I've got the situation where up here, you see a lot of A's I injected, and I can put in exploit code here, and I can jump back to it. But now I'm going to plan the appointment. Now you now control the app. You need to inject shellcode. The classic solution would be to put shellcode where the A's are and jump to it, but the operating system has address space layout randomization. So we need to find pop return. This will get us back to it. And you can do that by finding the text section with info proc map. That will show you the text section here. And you can view the assembly code there, and you can just look for pop return. And so one way to do that, which I did, was to use GDB to log the code. So you set logging on, and then I examine 2,000 instructions, and that'll create a file called gdb.txt, which lists everything. And now you can grep for return in there, and you can just look in there until you find a pop return. This one here contains pop return. So this is manually doing what we did with Mona on Windows. We've now found trampoline code that won't move because the text section is typically not randomized. So we just have to put in this address, and then we can pop back to an address on the stack, and this is something we've done before. So here's the structure of the layout. You have this ends up in the EIP, so you put in NOP instructions, shellcode, anyway. we've done. Now we're up to stuff we've done before. But that's a good project for you to do to practice trampoline code on Linux. And that's what I wanted to show you for that one. So let me stop this recording.